Okay, this video is going to talk about end behavior of graphs. In pre-calc, we've talked a little bit about quadratics before this. So now we're going to talk about polynomials. And what we want to know is easy ways to identify a polynomial. And one of the easiest ways, or most recognizable ways from a graph, is talking about end behavior. And again, it's going to relate a graph to a function. So generally, end behavior literally just means as we're going off to infinity or negative infinity in the x direction. So as we go to the right or to the left on our graph, and I'm not talking about the middle, like notice this graph in the middle here or down here where it's looping down to a minimum, or where all the kind of the action happens, right? Where all the swooping happens. I'm just talking about as we go to infinity, so the far right end of our polynomial, or to negative infinity, the far left edge, right, of our polynomial. Are we traveling up or down? Will it rise to both the left and the right? Or possibly fall to both the left and the right, or will we rise one direction and fall the other one? Now, there's an easy way to kind of recognize that. If the leading exponent, the highest exponent, what we call the degree of a function, right? If the degree is even, right? So this fourth power, or right up here, in the middle we had a sixth power, on the left we had a fourth power. If that highest exponent is even, both ends will travel the same way. If, on the other hand, notice down at the bottom, we have an odd exponent, so third power, fifth power, and over here would be x to the first power, notice both ends will go opposite ways. So let's talk a little bit about those fine-tuned details, because it will also matter what the leading coefficient is. Right? So what do we know about the end behavior of a polynomial just directly from its equation? Well, for an even degree polynomial, again, an example would be x squared, right? Where the highest exponent in the polynomial is an x squared, it's a 2, right? Or an even number. Both ends of my graph are going to rise. We're going to rise to the left, we're going to rise to the right. Right? Or as you go infinitely to the left, we're going to go up. If you go infinitely to the right, we're going to go up. Again, in the middle, it could be swooping all over the place. We could be doing just about anything. But we know the ends of my graph are going to go up both ways. Now, what if that even degree polynomial, though, had a negative leading coefficient? So notice up here for x squared, technically, our leading coefficient, right, was a 1, right, a positive 1 there. Well, what if it's a negative number, such as negative x squared? Well, remember, that's just a vertical reflection. So our two ends going up are now going to be going down, very simply. And again, that works for x to the fourth, x to the sixth, x to the eighth, any even degree, right, even exponent, right, the highest exponent in there. So we could even say if this was x squared, let's say plus 3x, or negative x squared, minus 3x plus 2, right? We could have a lot of other stuff happening. We're going to look at the highest exponent and the coefficient, the leading coefficient, the coefficient in front of the term of highest degree. Well, again, what happens if we have an odd degree? Well, what about something like x to the third, or x to the fifth, or seventh, or even x to the first, right? Well, think 1x to the first, or 1x to the third, we're going to fall to the left, we're going to rise to the right. It's almost like having a positive slope. Right? Again, if we had just x to the first up here, we would have a rising slope from left to right. We would be increasing the whole time. Okay? And again, if we put a negative in front of there, if our leading coefficient were a negative number, we're going to vertically reflect, and we would be rising to the left, falling to the right. Okay? Rising to the left, falling to the right. And again, you can have lots of other terms added on there. The one term that sort of rules the roost, the one term that rules the day, right, is that highest exponent. It's going to, as x gets really, really, really big, right, as we move way out to the right toward infinity, that highest exponent's going to sort of be the biggest thing in your polynomial. It's going to have the largest effect. Imagine even over here at the left, if x were something like 10. Well, 2 is still 2. 3 times 10, we're going to have a negative 30 going on here. That's pretty big, but again, 10 squared is 100. That leading term sort of gets so big so fast that those other numbers will sort of go by the wayside, right? Even if you plugged in something like 1,000, negative 3 times 1,000 is negative 3,000, but 1,000 squared is already 1,000,000. So we're going to add a negative million to something smaller than a million, like a 3,000, and even smaller, a 2. Those last two terms really aren't going to matter. That leading term is really what rules the roost. So you got to check the degree, the highest exponent in your polynomial, as well as the leading coefficient. Determine, are we going to sort of have a normal, a positive, leading coefficient? Both ends go up or down and then up, or are we going to have a negative leading coefficient, where now, if it's an even exponent, both ends go down, or basically we sort of fall, right, the whole time for an odd degree. In that case, let's try matching up these polynomials real quick, and let's just see how fast this is. You'll notice that each one of the graphs below is very unique. I've got this green graph where both ends are going up, the purple graph where both ends are going down, and then the blue and the sort of reddish-orange graph here where the ends are going opposite ways. And this is how fast it is. If we take a look at f of x up here, 5x to the third. Well, I know we're an odd degree, so I would say that f of x is either going to be this red graph or this blue one. Odd degree, right? And I'm ignoring the minus 4x squared. It's that odd degree, x cubed, that matters. Well, in a positive 5 tells me again we're going to fall to the left, rise to the right. I would say this red graph over here is a good one. Which other graph do we have that has an odd degree? Well, notice we've got a 6th power and a 5th power. That's an even degree. We've got a 1st power, but a 4th power. So again, that's an even degree. Now notice over here, we've got 5th power and 1st power, 5 being our odd degree, our term of highest degree. And a negative 3 tells me that's going to fit this blue graph very well. Negative 3, so rise to the left, fall to the right. Very much like a negative slope, just with sort of that action stuff going on in the middle. Let's go back to these even exponents. Again, if 4 is my term of highest degree, notice in front that would be a positive 1. I'm not worried about the negative 7. That's not the same term. My coefficient of x to the 4th is a 1 right now. And since that's positive 1, I would say the green graph is our best bet here. And notice negative x to the 6th, that looks a lot like our purple graph up here would be h of x. All we have to do is check that highest exponent and check out its leading coefficient. Is it positive or negative? And we can determine the end behavior on any graph. Are we rising or falling as we move both left and right? All right, I hope that helps you with end behavior. If you have any questions, make sure you talk to your teacher. Otherwise, have a great day.